Now, what is a transaction, or in this case, a database transaction? A database transaction is a single or sequence of operations performed on a database. Now, in our case, the issue can arise when multiple operations are being performed on the same row of data. Now, due to the concurrent nature of databases and the want for atomicity, consistency, isolation, and durability, and ACID is the acronym if you remember that from your database course, if you ever took one, a transaction either fully occurs or not at all. So, an example of all or nothing in our case, we want to make sure that the changes that are occurring with our funds data stay consistent and that each transaction is isolated from the other. We want to make sure that either the funds go through, whether it's deposit, withdraw, sending the funds over to another account, it either does it or it doesn't do it at all. Nothing halfway, especially when it comes to handling money. Now, to help in those scenarios of making sure it either occurs fully or not at all, we can utilize different types of locks. When a resource is locked by a transaction, it cannot be accessed by another transaction until the lock is released. So to handle the issue of multiple operations being performed on the same row of data, we'll utilize a lock, right? When one person is trying to access information from the table and either trying to read or write, we can apply a lock to essentially create a queue of requests to be able to make changes to that row, whether it's reading or writing, updating. If somebody already has access to that row, the next person has to wait, right? It creates that line of individuals or transactions that can occur on that row just to make sure that everything is consistent and every transaction is isolated. So how would that be possible in Spring Boot? Well, first we need to enable transactions in Spring with the transactional annotation. The transactional annotation is used to mark a method or a class as transactional. Any database operation performed within that annotated method or class will be executed within a transaction. It's going to be isolated. If the transaction is successful, the changes will be committed to the database. If an error occurs and the transaction is rolled back, the changes will not be persisted to the database. So there are fallbacks for cases where there's issue with a specific transaction. Now, transactional does come with metadata that we can adjust, such as a timeout amount to do a transaction, the isolation level, and even specifying what exception to roll back for or even not to roll back for. So we can determine based on what type of exception whether we want to remove the information that was attempted to be stored or just let it fail how it is. By default, though, transactional deals with runtime exception. So as you can see here, this is how we utilize the @transactional annotation. We can either put it above the class or we can either put it above the method. And then within this annotation, we can start adding some metadata such as timeout, such as isolation level, and the certain type of exception that we want to roll back on, which we'll utilize as we start to add it to our application. Now, I talked about isolation, right? Unfortunately, Spring allows us to specify the isolation level. And by default, it is default, which defaults to the isolation level of the database. So if we set the isolation level on the database, it will default to that. Now, isolation level is important because it helps fight against issues like dirty reads, which is a transaction that is reading from a row that was modified by another transaction that did not commit yet, meaning you're probably seeing old information. Or another issue like non-repeatable reads, which is a transaction that reads from the row multiple times and get different results each time. We don't want inconsistency. Now, the level of isolation Spring supports is default, which, like I said, it falls back to the database isolation level. We have read uncommitted, read committed, repeatable read, and serializable, each going from the lowest level of isolation to the highest. Now, the highest isolation level, which is serializable, prevents all concurrency problems because it executes sequentially, meaning it executes in order. But with a long line, it can take extra time, so it could affect performance. Serializable is what we'll be using because we want to make sure our transactions do not face any concurrency issues. So we'll have to sacrifice performance for consistency. Now, you can leave it as default if you know your database isolation level is enough, but we'll make that change in Spring in our case. So you have to decide what type of isolation level is important to you based on how you set up your information, right? If you care a lot about consistency and making sure that your information doesn't face concurrency issues, then serializable may be the way, but you may have to sacrifice some performance. And we also have propagation level. Transaction propagation level in Spring is the ability to maintain the integrity of transactions when multiple transactions are running simultaneously within a single transaction context. That's a mouthful. And the level of propagation Spring offers is required, requires new, supports, not supported, never, and mandatory. The level we'll be using is required and is the default propagation type, even if you do not select it. Required just means that all transactions after the current transaction requires a new session. Now, I won't be going over each one individually, but if you want to get more information about it, I'll leave a link so you guys can go read up more about it. But we'll be using required. Now that we have the transactional annotation and we talked about it, we can now utilize transaction locks. When dealing with money, making sure that we have the most current state is very important. Having multiple people withdraw at the same time, or the case where you may have a deposit before a withdrawal, can cause issues when making sure that the money amount is consistent. We usually want to make sure that the state of the data is as consistent as possible. And this is what we'll leverage transaction locks. And JPA has two main lock types defined: pessimistic locking and optimistic locking. Now, with optimistic locking, the transaction doesn't lock the entity immediately. Instead, the transaction commonly saves the entity state with a version number assigned to it. And it utilizes two threads to either read or modify the same data without blocking each other. So like I said, the database takes note of a version. It can utilize either dates, timestamps, hashes, and it checks whether that version either changed or if it hasn't changed before writing the record back. If the record is different, the transaction is aborted and the user is informed and they have to restart. If you want to enable optimistic locking in Spring, you're going to have to use a @ version annotation. If you haven't noticed already, Springboot is all about annotation, right? So each entity class must have a version attribute. Each table must have a version column. The type of version must be either numeric, such as integer, short, or long. So when a transaction attempts to read a record, it aims to ensure that the version attribute has not been changed by another transaction. If the version attribute is not changed, it will be updated. If the transaction noticed a change, the transaction either throws an exception or it retries. So here's a little look on how it will look like in your entity. You'll have a column called version, or whatever you choose to name it, but you have to use the annotation of @ version. And it'll either have to be long, it have to be integer, some type of numeric value. Then we have pessimistic locking. When we use pessimistic locking in a transaction and access an entity, it'll be locked immediately. The transaction releases the lock either by committing or rolling back the transaction. So we'll use pessimistic lock when you need to lock the record for exclusive use until you have finished with it. It does provide better security for dealing with concurrent changes, but there are cases where deadlocks can occur. So only until Bob gets out of the bathroom can Joe go inside of the bathroom. Both cannot go inside concurrently. But there is a case where Bob may have left the bathroom and Joe didn't realize, and now you have Joe standing outside the bathroom, not realizing that Bob is already done in the bathroom. It creates a deadlock. A deadlock is when two or more transactions are unable to proceed because they're waiting for each other to release resources. It's like waiting in line for the bathroom with no one in it. Now in Spring, it offers two types of pessimistic locking. It offers pessimistic read, meaning any transaction can read simultaneously, but updates or deletes are not allowed, right? Meaning I can read from a row, but two or more transactions cannot update or delete from that same row. Then there's pessimistic write. It's an exclusive lock, meaning that only one transaction can read or write at any time. No other transaction is allowed to perform read or write operations concurrently. This offers the highest level of isolation for records. So the same thing with Joe and Bob, right? If I'm in the bathroom already, only I can wash my hands. Only I can use the restroom. Everybody on the outside has to wait until I'm done. Which one will we be using? Will we be using optimistic? Will we be using pessimistic? Well, in our case, we'll be using pessimistic locking. So if you haven't realized already, pessimistic locking is more suitable for systems where data conflicts are frequent. For instance, in a banking system where account balances are frequently changing and updating, using pessimistic locking can prevent conflicts and data inconsistencies. So when you have multiple threads that may manipulate data on the database, this is perfect. It's great for dealing with concurrency. I hope you guys got a better understanding of transactions and transaction locks and why we'll be utilizing pessimistic locking over optimistic locking. If you have any other questions, you can let me know. But in our case, we'll be using pessimistic locking. Now here I am back in IntelliJ, and you're probably thinking, do I need another dependency? And no, luckily you will not need another dependency. Luckily, this dependency right here, which is Springboot Starter Data JPA, will configure a data source for us. And it will configure transaction management for us as well. So we have access to transactions without having to make any additional configurations. So now that we already have the needed dependencies for transactions and dealing with transactions, all we have to do is start adding those annotations to our services and our repositories to make sure that our application know when to use transaction locking. All right, so now that we have an understanding of transactions and transaction locking, we can go ahead and start using the annotations, such as the transactional annotation and the lock annotation, to help fight against concurrency issues. So what I'm going to do is I'm going to start off from the user service and we're going to make our way to the other services. And then after that, we can go ahead and start adding the business logic once we add the proper transactional annotations and the proper locking annotations to the rest of the services. Now, remember I said that you can add the transactional annotation from multiple areas, right? You can add it from the class level or you can add it from the method level. But it's better to use the transactional annotation from the method itself just for more control. Now to start off, I'm going to work on the get user by email. Now with this get user by email, I'm not really expecting too much because we're not going to be writing any information to the database, which is good. We're just going to be retrieving information from the database, and we want to make sure that the information that we're retrieving from the database is the correct information. And luckily, with the default metadata that transactional provides, that is possible. So with the at transactional, and I'm going to do that at transactional and import that, the default isolation level will be, guess what? The isolation level of your database. And by default, I'm using Postgres, and usually the default isolation level is read committed. And the default propagation level is required. So for this case of just getting user by email, that should be enough because with read committed as the default isolation level, it works just fine because it prevents dirty reads, meaning the application will only read committed data. Now, the only thing I really want to change in this metadata is the fact that we want to specify that this is going to be only read only because like I said, we're not making any writes using this specific method, right? We're just getting the user by email and we can inform the database that this is going to be only read only. And that does help with performance because the database knows it doesn't have to worry about writes anymore. It just has to worry about reads. And it's going to be the same logic for this second method of getting a user by ID, right? Because it's still going to only be a read type of transaction, but we're not going to be writing to the database with get user by ID. So it's better to keep the default transactional metadata of the isolation level and the propagation level, but as well as informing that it's going to be only read only. Now, the next method I want to set the transactional annotation for is the save user. So when it comes to saving a user, I also want to keep the default metadata. The default isolation level, like I said, is read committed, which prevents dirty reads. So if a user is created and the data is committed, the application can read that is committed and handle accordingly by throwing an exception. And by default, the Spring at transactional method will only roll back on unchecked exceptions such as runtime exceptions, but you can configure it, which we'll do in a couple of minutes, to roll back for custom exceptions. So let me go ahead and add this at transactional here. And like I said, we're going to just keep the default metadata. But in the second case of sign up user, there may be a case where we're unable to save a user. Maybe there's an issue while saving the account or an issue while saving the user. We want to make sure that it rolls back the information properly. And like I said, it's only going to roll back for unchecked exceptions, such as runtime exceptions, but I have to configure it to roll back for a regular exception, a checked exception. And the property that I'm going to use is roll back for, and I'm going to set that equal to, got to open up some brackets and do exception, two colons, class. So it's informing that when I see or when this sees an exception, right, go ahead and roll back any transactions that occurred, right? It's going to go back to the original state. So maybe there was an issue while saving this account. Well, if there's an issue while saving the account and an exception was thrown, go ahead and roll back the user as well, right? We don't want to continue the transaction if there's any issues while creating the user. So that's all the transactional annotations that we'll utilize here. Don't necessarily have to use locks in this case, right? Because in this case, we're only getting user by email, getting user by ID, and we're only going to save a user if there isn't a user in the database already. And we know that with the default propagation and isolation level, we don't have to worry about dirty reads. So if the user is not committed, then we can go ahead and try to save the user. And if so, if there is already a user in the database and we read that information, it's going to go ahead and throw an exception and we're not going to be able to create a user. So when it comes to the isolation level and the propagation level, we don't have to do anything too strict in this case. Now, the next service that I want to work on is the account service. And here we have a couple methods of save account, delete account, find account by ID, and create account. And we need to start establishing how strict we want to make the isolation level, the propagation level, or even if we want to consider adding some locks. So one thing to keep account is that when we created the account repository, we created a method called find by user ID, which is able to retrieve the accounts based on the user ID, right? All the accounts associated to a specific user, it will go ahead and retrieve those accounts. So what we have to do is in the account service, we have to utilize that method to retrieve those accounts. And we have to make sure that those accounts data stays the same, right? Because if we want to configure information regarding those accounts, or if we want to make sure that the balance stays the same, then we're going to have to configure some locking and utilize transaction to make sure that the information stays consistent. So let's go ahead and add that. So when it comes to getting information, I usually try to keep that up top. And honestly, let me just move this find by and move it up top. And below that, I'm going to do fun get accounts. And it's expecting a user ID as the param. It's going to be of type long. And what I expect is a list of accounts. And it could be nullable, meaning there are no accounts associated to the user. And then what we can do here is just return account repository dot find user by ID and then just pass in the user ID. So that is the function. So this will be able to get the accounts associated by a user. And then what we can do is we can start working on what we think is the proper lock and what we think is the proper metadata for the transaction. So in this case, it is possible to add a lock and it is possible to add transactional. There are two separate annotations for it. And we talked about pessimistic reads, we talked about pessimistic writes, we talked about optimistic reads, optimistic write. But due to the nature of this application, we're going to use mostly pessimistic related locks. And in this case, I want to apply a pessimistic read lock to this query, which will prevent other transactions from making any modifications to this account while reading the data, right? Because when I'm reading the account information by a user, I want to make sure that that balance stay consistent. So a pessimistic read is useful when you want to ensure that the data stays the same during the read. So like I said, when you need to check the account balance before making a transaction. And I'll also use the add transactional annotation to ensure that the changes are committed consistently. And in this case, this is still going to be considered a read-only action because I'm just retrieving the accounts. I'm not going to be writing any information from this specific method. So we're going to specify in the metadata that this is going to be read-only just for a little bit of database optimization. So remember, just as a disclaimer, locks can and will block other operations. So if that's not what you want or if that's not what is needed, think before using it because it could affect performance. So to utilize a lock such as pessimistic read, you can do @lock, import that, open that up, and specify the value is going to be equal to the lock mode type dot, and you can see that there's different types of locks. So there's optimistic, there's pessimistic write, read. There's even a pessimistic force increment, pessimistic force increment, but I'm just going to do pessimistic read. And then I'm going to utilize a @transactional. And I'm going to specify inside that this is only going to be read only and set that equal to true. Now we have the ability to retrieve accounts based on user ID, and we're making sure that that information stays how it is while we're reading that information. Meaning if there is a write to that account when we're reading it, then it's going to go ahead and inform the person trying to add information to that account that, hey, right now this is locked. You can't add anything or you can't deduct anything. We're making sure that the person trying to read this gets the most valid information regarding these accounts. Now, if that's not what you want, then you're going to have to find another approach for that. But if that sounds accurate, like you want to make sure that you have the most accurate information and making sure that other actions can't change that, then this is the proper approach to take. The others should be pretty straightforward now. So when it comes to finding an account by ID, what we could do is do transactional, and we can just inform that this is going to be read only. and we're going to set it equal to true. And same thing, right? We can use a pessimistic read here just to make sure that, while we're grabbing this account, make sure that it stays the same. Nothing can change it until we're done reading it. Now, when it comes to saving an account, this is also going to be interesting, right? Because when we're saving an account, meaning whether it's a deduction, whether it's an addition, we want to make sure that that information stays consistent. So we're still going to utilize transactional. But when it comes to locking, we want to make sure that nobody has the ability to read information and nobody else has the ability to write information. So to me, that sounds like the perfect thing to utilize is pessimistic write because it is a locking mechanism that ensures exclusive access to a piece of data. So it prevents concurrent updates. So whether I want to add money to this account or whether I want to subtract anything from this account or any other type of change to this account, I want to make sure that I have exclusive access to this account. So what I could do is add a lock, and that value is going to be equal to lock mode type dot pessimistic right. So like I said, disclaimer, when you're using a lock like pessimistic right or pessimistic read, you have to understand the trade-off, right? Especially with pessimistic right, because like I said, it is an exclusive lock. And with something like an exclusive lock, things like deadlocking can occur. And using pessimistic right does increases the chance of that happening. So when you're using these type of locks, you have to make sure that you understand what you're getting yourself into and the trade-off that you have with performance and things that can occur and how to handle those properly. So always do research and have a better understanding of why and when to utilize this stuff. So when it comes to money, it is good to establish a lock. It is good to make sure that you have exclusive access because you do not want other individuals making change to that account while you're making that change, whether it's because somebody else may have, or even you in this case, is already deducting money. You don't want somebody else to be able to deduct even more money than the account even has. So making sure that you have exclusive access and making sure that you take money from the account first before somebody else does and being able to handle that accordingly is very important. So you have to think about the scenarios and the trade-offs when it comes to utilizing locks. Same type of logic with deleting an account, right? We want to make sure that we don't want any other transactions occurring at the same time when we're deleting an account because we're deleting the account, we're getting rid of it, and we don't want money being added to the account and then we're deleting the account at the same time. That could be a problem because what about the money, right? So we want to make sure that when we're deleting the account, we set a lock on it to making sure that there aren't any concurrent transactions that occur on this account before we delete it, right? We want to make sure that before we delete the account, we make sure there's no money on the account. We put it into another account if possible, and then we go ahead and delete the account. Or we can have a check beforehand to make sure that the account has no money on it to inform the user that if you want to delete this account, then you have to deduct all the money on the account and then you can delete the account. So maybe they might have to do a transfer before deleting the account. But you want to make sure that the information is consistent and that it is containing the value or the amount that we expect it to have, right? So that when we transfer the money and that we see that it's zero, there isn't another transaction coming in that may affect that value of the account. We can delete it as expected. So we're still going to utilize the pessimistic right in this case. So I'm going to utilize the lock of, you know, value equal to pessimist or lock type, lock mode type dot pessimistic right, and still going to utilize at transactional. Now, finally, with the create account, we're just going to use at transactional. It doesn't really need to be a lock in this case, right? When it comes to creating an account, we're just going to go ahead and create it because I already know that the UUID is going to be unique. So if there's another account that's being created, most likely it's going to have a unique name anyway. So we don't really have to worry about that. So in the case of creating an account, unless we're logged in into multiple computers, which we'll check, right? Because we're going to be utilizing JMeter to check how this application handles these locks properly. But in the case that there's multiple changes occurring on the same row, then the lock will just handle that as expected, right? It's just going to say, hey, just one at a time. The rest can is going to have to try again later. All right, so now that we handled all of these methods in the account service, we can go ahead to the last service, which is the fund service. All right, so here in the fund service, we can go ahead and get started. But before I really get started on the transactional annotation for each of these methods, what I want to do is I want to extract some of this repeated code because repeated code is no good. If I see the same thing being used multiple times, then that just means that it's time to extract that. And we can create a method called create transaction to create a transaction, because I know that each one of these methods is going to have to create a transaction. And in the future, honestly, some of these methods are going to have to create multiple transactions. So it's better to have a method that we can just call to create a transaction or to return a transaction that we could just save. So what I'm going to do is I'm going to create a private function here, and I'm going to call it create transaction, and open that up and open up the curly braces. And when it comes to extracting our repeated code, what we have to do is we got to look at the repeated code and see what is the similarity between these calls, right? What exactly are we utilizing in each of these calls that make the transactions, or in this case, the transactions or the creation of the transactions all the same. So in this case, I'm seeing user ID all the time, I'm seeing the amount all the time, I'm seeing the transaction type all the time. So what did that mean? I got to take those as parameters and create and generate that from within. Then there may be cases where I might need some fields like to account ID and from account ID, and I can take that in as a parameter, but I can also make that optional because we may not need to utilize that for all transactions. So that's exactly what I'm going to do. So the first one is going to be user ID. That's going to be of type long. The second one is going to be amount, and that's going to be a double. The next one is going to be transaction type. It's going to be of type transaction type. And then the optional, right? There's going to be to account ID. It's going to be a type long. It's going to be equal to null. And then there's going to be from account ID. It's going to be a type long. And that's also going to be optional. It's going to be equal to null. So in the case where we're not going to use it for specific transactions like, deposit or withdraw, well, it'll just have a default value of null, and we can just, let that sit and not utilize it. But all of these are going to be utilized in user ID because we have to save who's making the transaction, the amount, and the transaction type. That's what I see correlates to all of these transactions. And then from this create transaction function, what we could do is, obviously we know we're going to return a transaction, so we can specify that here. We can also call it infer it, but just for readability. And then from here, what I can do is create a variable called transaction and set that equal to transaction, an instance of transaction. And what I can do is start, and I forgot to put transaction to C. And what I can do from here is just start passing in the value. So I can do transaction dot user ID, and that's going to be equal to user ID. Transaction dot amount, it's going to be equal to amount. Transaction dot transaction type is going to be equal to transaction, the whole transaction type, because luckily we used a parameter. And if I go into it, just because it's going to get the value by using these enumerated, it's going to get the value for us. So we don't have to specify the specific value of the transaction type. And then transaction dot to account ID is going to be equal to account ID. So if we don't specify a value, by default is null. That's fine in this case. And the same thing for from account ID. It's equal to from account ID. So cool. Now we have a method that creates a transaction for us. We can go ahead and place that into each of these methods, and it will save us time. But we also got to return the transaction. So return the instance of that transaction, and now we can go ahead and pass in the parameters whenever we need it, and save that instance that is returned from this method.